So for distance vector, again, we're starting with the assumption that our costs are in the number of hops it takes to get to a destination. We have a starting condition. That we know about our directly connected neighbors. We also must remember that this is run on every router. So let's go and take a look at what an example network might look like. So here's an example network. I'm going to zoom this in a little. And this is a tape that looks at the entire state of the network. Realizing that this entry right here for A, that would be just what's in itself. It would be what's in B, and so on and so forth. No single router is going to have a full picture of all of the distances that each router might take to get to a destination in the network. That's going to be something that is distributed across here. So let's look at how things would look at the start of distance vector. And we're going to start by looking at A. So all entries that appear in here, A will have a distance of 0 to itself. It's just the way the algorithm works. Same thing would be for B, would categorize itself as having a distance of 0 to itself, and you could go ahead and you could fill that in for all of them. Now, as we said, A will know about all of its directly connected neighbors, and so we would put a 1 in for B, a 1 in for C, and a 1 in for F, because those are all, and a 1 in for E, because they are all the directly connected neighbors for A. And then D and G are going to get infinity, not necessarily because A knows about them, but we, with our God's eye view of everything, know that they're there, and so they have a distance of infinity and cannot be currently reached. And so what would happen is that this would be the distance vector that A would announce to F, E, C, and B. And each one of them would have their own unique distance vector that they would announce back. And so what I want you to do at this point is I want you to go ahead and fill out the rest of this table. And then this, with our final answer, is going to be submitted as kind of a attendance check for this lecture. The second half we'll go over in a second when we finish off filling out the distance vector. So let's look at some of the steps and how this distance vector would progress. So I'm going to keep my work so far. and we're going to look there. So for B, just to give myself something to work with, B would say that it can reach A at a hop of 1, it can reach C at a hop of 1, and everything else is going to be at a hop of infinity, as they are not directly connected. And so if I went through the exchange between A and B on information, there's not much that's going to change here, because we can see that A already has a good route to C, and B doesn't have a better route. Where things are going to get interesting is when we look at what get announced for for C. When C announces to A its information. So the big thing that's different for C is that D is at a hop of 1 from C. And so when C announces to A, what A is going to do is it's going to go, okay, I can update my distance vector right here, and I can say that that's now a hop of 2. Because A to C is 1, and C to D is 1, so that should come out to a cost of 2. And there's the potential for this to change again. It depends upon when the packets arrive, who gets there first, that sort of a thing. And so through this process, once you have all of the initial distance vectors going, you can start spreading around that information. And so eventually what we'll end up with is we will end up with the completed distance vector for A, which I'm going to fill out right now. I'm just going to do the A part. So the final distance vector for A would also have in here at a cost of 2. And so this is our final distance vector after the network is stabilized. So after the network is stabilized, this is the final distance vector, and A will always advertise what this is. And so for the second part of what I want you to do, so that you can prove to me that you've done this, is you're going to have the table file for the starting and the final. And then there will be, so put this in some nice, easy to read, think image, either JPEG or PNG. You can upload if you want to do an Excel table too. or something in Word. Make it easy for me to read, and there will be a link on board. And this won't be a graded thing. This is just kind of attendance check. Are you paying attention? Are you watching the videos? And I'll put these periodically throughout our remaining video lectures throughout the rest of the semester. So that is basics for distance vector. Next video will cover some of the challenges that are faced by RIP in the practical implementation of this protocol.